What's going on? So today I will be going through the Berry phase of spin-half eigenstates in a magnetic field. So you might have remembered that in the previous video we went through the spin-half eigenstates in a magnetic field. So let's just quickly recap what that was. So in the previous video, when we were given a Hamiltonian, that is this magnetic field dot the Pauli vector. If you're unsure of what this is, please check out the previous video for a quick recap. Where the magnetic field, if we express it in polar coordinates, so there's a magnitude here, then sine theta, theta is the polar angle, cos phi is the azimuthal angle. Basically, this is spherical coordinates. If we express the magnetic field in terms of spherical coordinates, then the resultant eigenstates we get are the following two eigenstates. First of all, we have the spin-up eigenstate, which I also call the plus eigenstate, denoted by this bracket notation, which is given by the following expression here. So remember that the angles theta and phi came from the magnetic field. They came from the angles the magnetic field is pointing in. And that is the plus eigenstate, the spin-up eigenstate, and then there was a spin-down eigenstate, which was given by sine theta over 2 minus e over I phi cosine theta over 2. And these are the normalized eigenstates, which means that so these are the normalized eigenstates in the quantum mechanical system. So these are the eigenvectors of the Hamiltonian operator. And normalized basically means that their norm is 1. Same for the minus eigenstate. So in this video, we will investigate what happens if the magnetic field changes in time. So in the previous video, I said that currently the magnetic field is just a static magnetic field. It does not change. But it turns out it is possible for experimental setup to have the magnetic field that varies. And when the magnetic field varies, it's natural to consider what happens to the eigenstates, what happens to the particle. And in essence, in short, when the magnetic field varies, the eigenstates each accumulate something known as a Berry phase. And this Berry phase has been studied greatly because it has a lot of properties related to the gauge structure of quantum mechanics or something. So I will not go too much into the detail today, but I will cover the basic calculation of the Berry phase for the spin up eigenstate, which is denoted this, and spin down eigenstate. So today we'll be calculating those two quantities, and yeah, so let's quickly consider what happens when the magnetic field varies. So as you can see, the Hamiltonian is a function of magnetic field, where magnetic field is a vector, a tree vector, because it has three components. So since the Hamiltonian is dependent on the magnetic field, when the magnetic field changes, the Hamiltonian will change. So if we have a magnetic field changes, if the magnetic field changes with respect to time, then we have a Hamiltonian that is dependent on the magnetic field, which is then dependent on the time. And when we have this, we have Hamiltonian that depends on time, we need to solve the time-dependent Schrödinger equation. And in 1984, Berry, in his 1984 paper, highlighted that this psi will accumulate something known as a Berry phase. So I will not go into the derivation of Berry phase in this video, but it is certainly a consideration for another video. And I will just give you the result. So what Berry found out was that when you solve this, you get psi as a function of time, is equals to e to the power of minus I over h bar integral of 0 to time t of the eigenenergy, and eigenenergy is dependent on the magnetic field, which is dependent on the time, and e to the power of I gamma n of t, and this is just an eigenstate of the Hamiltonian. So with this result, let's investigate what is in the following terms. So we have this term over here, and we have this term over here, and this is just the eigenstate at time t. So the first term here is called the dynamical phase vector, and the second term over here is the Berry phase vector. And this is of interest because when you integrate in a closed loop, and I forgot to mention one important thing previously, the magnetic field here must vary slowly with respect to time to ensure something called the adiabatic theorem applies. So that's a footnote that we need to note, that B must vary slowly in time, must vary very slowly, and in the limit that t goes to infinity, you get this structure over here, you get this result over here. So so the result of Berry's 1984 paper is that when you have this gamma n of t, when you have the when the quantum state undergoes the cyclic evolution, which means that it goes in a cycle, which means that the magnetic field, originally, let's say this is the magnetic field, it goes around in 3D space, and it reaches back the original starting point. Basically, B of 0 equals to B of t. And B is a vector, always remember that. So when it undergoes cyclic evolution, gamma of n, the Berry phase, is then equals to I, the closed loop integral of the eigenbra, then the gradient in the B space, in the parameter space, dot dB. So if we break down what each of the terms mean over here, first of all, gamma is the Berry phase, and the subscript n is the eigenstate, it's the label for the eigenstate. So n labels the eigenstate. Then we have a closed loop integral, because C is the integral, C is the path that the magnetic field takes in a cyclic evolution. So it's a closed loop integral. Then we have the n over here, which is the eigenstate, and gradient of, and right now we are integrating within parameter space. So this is a parameter space. We are integrating within parameter space, and in this case, because the magnetic field is three-dimensional, this is a 3D parameter space. 3D parameter space, yeah. So this is one way of calculating the Berry phase, and because it turns out that this is not the only way to calculate it. Because currently we are using a 3D parameter space, in this case magnetic field, but it could be any other parameter space that has 3 dimensions. Because we are using a 3-dimensional parameter space, we can apply Stokes' theorem and get another form, which will be something like this. I can't fully remember the form, but yeah. So you can use Stokes' theorem to get a form that might be easier to work with, and indeed that is what we're going to do in the future videos that come. But in this case, we will just calculate it directly from this formula. So this is the expression for Berry phase. Let me just box it up. So we'll refer back to this equation quite often in this video. So let's move on. So we can see that first of all, the Berry phase is calculated for each eigenstate. So for the plus eigenstate, there will be a Berry phase, and then for the minus eigenstate, there will be also a separate Berry phase. There will be different Berry phases. Berry phases, yeah. They'll be different from each other. So we'll first calculate it for the plus eigenstate, the spin up eigenstate. So for Berry, we'll begin our calculation. Berry phase for spin up eigenstate. So for the Berry phase for the spin up eigenstate is given by, so first of all, let's recall what the spin up eigenstate is. It is this two vector, a complex vector. Of course, you can add a phase to this and it wouldn't change the Berry phase. So then we have the gradient in three-dimensional parameter space of that. So the gradient, we can see that we need to calculate the gradient of the eigenstate. So calculating the gradient of the eigenstate is equals to the partial derivative with respect to radial component plus the plus 1 over r, the partial derivative with respect to the theta, which is the polar angle, yeah, that's the name, and 1 over r sine theta partial of the plus eigenstate with respect to phi, the azimuthal angle. And so if we evaluate this, we substitute this in here. We see that there's no r dependence, so the r cancels out. Then we will get 1 over r, and then there is theta dependence, so there'll be 1 over r minus half sine theta over 2, half e to the power I phi cosine theta over 2, and that is theta hat. And then we'll add, it will be plus 1 over r sine theta, and then phi, there's no phi dependence in the first component, so it will be 0. And for the second component, we will bring down I, and sine theta over 2 stays the same. So this is just evaluating the partial derivative by substituting the plus up eigenstate into this equation for the gradient. Then we can have, then we see that in the calculation we also need to take the ket of the eigenstate. I mean the bra of the eigenstate, the Hermitian, the conjugate transpose. I mean, and that would be cosine theta over 2. That doesn't change because it's real. And e to the power minus I phi, because this is the conjugate of e to the power I phi, sine theta over 2. So with this expression, with this expression here and this expression, we can multiply the two of them together, and what we will get is plus eigenstate gradient plus eigenstate equals to 1 over r minus half sine theta over 2 cosine theta over 2 plus half sine theta over 2 cosine theta over 2 theta hat. This is just multiplying this component with this, and you see that it cancels out, so this is just 0. And then there's also this phi unit vector over here, and that will be 1 over r sine theta I sine squared theta over 2 and phi hat. So the first term cancels, leaving us with the second term. So then, so the next one we need is the differential of b. And because we are working in polar coordinates, the gradient was the polar coordinates. So dB equals to dr r hat plus r d theta theta hat plus r sine theta d phi phi hat. So then if we take the dot product of this with dB, we will get I sine squared theta over 2 d phi. Because r sine theta appears here, r sine theta here appears here, and they cancel, and the result, and theta hat dot theta hat is 1. And then, yeah, so this is the final expression. So then we can express, if we will express this in double angle formula for reasons you'll see later. So this can be expressed as I over 2 1 minus cosine theta d phi. Alright, so finally we now have this entire region here. We have this expression here. We need to take the integral and multiply by a factor of I. So the plus eigenstates Berry phase accumulated over a cyclic evolution with, over a path C is equals to I closed loop integral of I over 2 1 minus cosine theta d phi. And this is then minus half integral of closed loop integral 1 minus cosine theta d phi. And right now I'm just going to assert that this is equals to the solid angle. So this is the solid angle of this path C. So I will show, so right now this step might be a bit confusing and it's not exactly clear right now, but I do intend to create another video detailing this step over here, as well as another step I will go use later on. So yeah, if you want the video, please leave it in the comments below. So what do we see here? We see that the Berry phase, the final expression we get is that the Berry phase of the plus eigenstate is minus half times the solid angle. This is the final expression. And what this means is that let's say we have the magnetic field. So remember in the previous video I mentioned that the Bloch sphere and the magnetic field share a lot of similarities in the sense that they sort of live on the same coordinate system. So if we have a Bloch sphere, let's try to draw a nice Bloch sphere here. Oops, it's a bit out of shape, but I think it should be fine. If we have a Bloch sphere here, and let's say we have a magnetic field, let's denote the magnetic field in red. So let's say we have a magnetic field that varies from here, and then let's say the magnetic field varies in a fashion like this. Yeah. Then right now the magnetic field is parameterized by the angles theta and phi, right? And of course the magnitude of it, but because what we have found out is that the Berry phase depends on the solid angle of this region, this curve C. This is the parameter curve, the parameterized curve C. The Berry phase depends only on the solid angle. So in a sense, we can project it down onto the Bloch sphere, and we project this parameter, this is if we project this curve C, this path C onto the onto the block sphere, sorry. If we project it, we'll get something like, yeah, you just have to imagine that projects onto the block sphere. Okay, maybe I can draw that better. So this is living on this. So if we project path C onto the block sphere, we get basically a path traced out by the plus eigenstate. So the plus eigenstate is living on this, is a vector pointing to the surface of the block sphere, and is aligned. We learned in the previous video that the plus eigenstate is aligned with the magnetic field all the time. So in essence, what we can tell about this is that the plus eigenstate's Berry phase is just minus half times the solid angle traced out by the magnetic field, or the plus eigenstate. And this is once again the magic of the block sphere, because the block sphere gives us a very nice geometrical picture of how the Berry phase behaves. So once again, the block sphere first allowed us to translate the two-component complex vector to a three-component real vector, and a three-component real vector lives on the surface of the block sphere. So the block sphere first gives us that nice picture where it aligns, where the plus eigenstate aligns with the magnetic field, and then secondly, it gives us a visualization of what the Berry phase of a plus eigenstate looks like. And soon we'll learn that it applies for the minus eigenstate as well, once we find out the Berry phase for the minus eigenstate. So then so I hope that the Berry phase for the plus eigenstate is clear. And now let's move on to the calculation of the Berry phase for the minus eigenstate. So for the minus eigenstate, let me just see. So for the minus eigenstate, we first write out the minus eigenstate, which is sine theta over 2 minus e of I phi cosine theta over 2. Now most of this derivation is going to be the same, so just feel free to skip ahead if you want. Then we take the gradient, which will be zero minus and then we take the bra version, we take the the conjugate transpose, and then we multiply the conjugate transpose with the gradient of the eigenstate, and we get very similar expression to that of the plus eigenstate, but instead of sine squared is cosine squared. And yeah, then we can multiply this by dB, we get I over 2 1 plus cosine theta over 2, where we have applied the double angle formula, the half angle formula, whatever. And so if we integrate around a closed loop, we get that the Berry phase for minus eigenstate along a path C that is cyclic is the closed loop integral, because it's a closed path, a cyclic path, I over 2 1 plus cosine theta phi cosine theta, I mean, d phi equals to minus half closed loop integral of 1 plus cosine theta d phi. And this, so previously we had an expression that looks like 1 minus cosine theta d phi, right? We had this expression. And then we said that this was equals to the solid angle of C. But now we have a 1 plus cosine theta instead. And so what is going on over here? So it turns out that if you evaluate this, from my calculations, I've found out that this could be equals to either 4 pi minus the solid angle, or the solid, or minus the solid angle. So this is in a case where the C encloses the top of the sphere, which is the point where theta equals to 0 point. And this is the case where it does not enclose point. So of course, this step right now, this step from here to here is really confusing, and it took me some time as well. But so I'll not go too much into detail over here. But if you want me to cover it in another video, it's definitely on my to-do list. So in each of these cases, we'll see that it's either equals to minus 2 pi plus half of the solid angle, or half of the solid angle. And in this case, because it's a Berry phase, and in the end we're going to take e to the power of I gamma, so this 2 pi over here is essentially it can be taken away because it's going to be a phase. So this step might seem a bit sketchy, but I'm going to cancel it because the only place we're going to use the Berry phase is inside the phase vector e to the power of I gamma. So this justifies the cancellation. So in the end, what we get is the Berry phase of the minus eigenstate in a closed path C is equals to half times the solid angle subtended by the path C. So yep, let's just box that up. So in the end, remember that the solid angle is the solid angle of the magnetic field. So yeah, so right now, so once again, if we bring back the block sphere picture, so remember this equation is half times the solid angle. If we bring back the block sphere here, if we have the magnetic field in this going in this cyclic evolution, and let's say it results in a solid angle, then the minus eigenstate will also, although it aligns like in a opposite direction with the magnetic field on the block sphere, when the minus eigenstate is projected onto the block sphere, it's converted into the block vector, it will be anti-parallel with the magnetic field. But in the end, the Berry phase of the minus eigenstate is still half times the solid angle subtended by the path C of the magnetic field, and you can see that equals to the path taken by the magnetic field. So the block sphere really gives us a clear interpretation of what happens of what the Berry phase, how the Berry phase can be represented on the surface of the block sphere. Is the solid angle traced out by the eigenstates. So then, now that there's so in conclusion, we have the eigenstate, the plus eigenstates Berry phase is equals to minus half times the solid angle of the path C, where C is the closed path of B field in parameter space, where in the three-dimensional parameter, and in this case the parameter space is the magnetic field space, the space of all magnetic fields. And then the minus eigenstates Berry phase is half times the solid angle. So this does not come at a coincidence. In Berry's paper, in Berry's 1984 paper, he also he calculated the Berry phase for a general spin S or spin J. Yeah, spin S. He calculated the Berry phase for a general spin S eigenstate, and he found out that the Berry phase is equal of a spin n eigenstate is equals to minus n times a solid angle. So you can see that n in this case, n equals to minus half, because it's a spin down, and we are talking about spin half systems here, so it's spin is minus half, and then this is the spin half up, positive. So when you can see that Berry's result, or rather our result here, agrees with Berry's result in his paper, but of course his result is more general because it's for a general spin n. We will go through this in the future, but I just want to do a quick calculation today for that. His method was different though, in that he used Stokes theorem, and yeah, but yeah, that's all I have for today. In essence, I just wanted to go through the calculation of Berry phase in the direct sense, because in Berry's paper he went through the calculation of Berry phase using Stokes theorem, and that's in the case of three-dimensional parameter space. Of course, the magnetic field is a three-dimensional parameter space, but I wanted to apply this formula directly to the spin half eigenstates, because we have the expression for the spin half eigenstates and we have the expression for gradient. So I thought that it would be neat to show in this video that that the direct calculation indeed agrees with Berry's result in general. And also, I would like to highlight this important geometrical picture, that the Berry phase is proportional to the solid angle subtended by the path of the magnetic field. So because the magnetic field has close relationship with the Bloch sphere, in the sense that spin half eigenstates, when expressed as points on the Bloch sphere, they align with the magnetic field. So we get a very nice picture that we get a very nice picture that the Berry phase of eigenstates is directly proportional to the solid angle subtended by the eigenstates when they are on a Bloch sphere. So yeah, this idea is an idea I'm also pursuing in my current research topic, so I thought it would be good to cover this. So yep, I hope that this video has been clear enough, and I'm sorry it was a bit drier today. So if you have any comments, please leave it in the comment section, and if you like this video, please leave a like and subscribe. So yep, that's all for today. Have a nice day.